So good afternoon. Can everyone hear me? So is quality good? My name is Praemassing. I'm working for Infineon, located in Austria, and I'm acting as a system architect for microcontrollers. I used to be an analog designer, by the way, and still in my deepest heart, I love analog, therefore I enjoyed this session very, very much this morning, Jens. I think 15 years back there was some lack of system architects in the company, and I said, okay, why not give it a try, since I'm looking more from a system perspective of the solutions rather than from a deep knowledge perspective. Not regretted yet. So you're still young, you still have to shape your future. System architect really makes fun because you bring software and digital and analog and power, you bring it all together. So it's about how to make systems, power and performance efficient. And it's very linked also to power. So power management, I used to say, you don't see it, but be aware it's always there. It's working behind. If you notice it, then we have a problem, so better you don't notice it. And in this presentation, I give you some insights on what are the main innovation drivers and what are the challenges and how solutions might look like to achieve this efficient power and performance. So three examples. One is a data center. I touch it a bit because Bernhard put scope on that one. I put more scope on the automotive. And then finally, I give also an outlook on robotics, which is getting a very hot topic. So power management as such is, I would say, a very essential building block in all electronic circuitries, and has become more and more a critical and very important component, because yes, it defines really decisively the performance per power, and that's really the asset. It's not only the performance, not only the power, but both of it. And why is it so important? Because it defines the cost. And in a business, cost is really relevant. So, and power management, what I love about power management is it's so diverse, right? Also, Bernhard, you showed it. So the range of input voltage can vary from kilowatt down to microwatt, and volt and current the same. And sometimes it's not only about efficiency, but efficiency is important because else electrical power gets turned into heat, and this we do not want. But there are other capabilities which are important. Think about reliability, think about safety, think about security, or EMI. And those are requirements which are important in automotive and also in robotics. So let's start with AI and data centers. Since there's the need for training the large language models on data centers, this really becomes a challenge for the data centers. And on the left, this is Jensen, so he's the CEO from NVIDIA. And this year, February, I think it was, or January in the CSS in Las Vegas, he already forecasted the compute performance where it will go to. The main driver is physical AI, and look where we are today, and look where it goes to, and we are already in the journey, but still it goes up and goes up. And you are much younger than I am, so you still have the possibility to contribute and to shape it. I think this is a really exciting time to get an engineer. On the right-hand side, similar numbers to what I saw in your presentation, Bernhard. It shows somehow what is the power consumption, how it increased over the years of GPUs. over the last 5 years. So I think interesting is that with each generation, the power consumption increased by 50%, and it will go up like this. Yeah. And it's tremendous, it's incredible. I know about numbers, not on the slide, but it tells if it goes up like that, we will have electricity need just for data centers by 7% of the overall global need. And put this into perspective, this is the electricity need of a country like India. So it cannot go on like this, so we need more also efficiency in the models, and I'm sure it will come. I will show you how the AI is powered, and it's done in 3 steps, from the grid to the core of a GPU. GPU typically runs on 1 volt, 0.7 volt, and I skipped the first stage from the grid to the 48. But from the 48, I think it's quite interesting. It's handled in 2 stages. And you see in the middle, there is this IBC, also mentioned by you, Bernhard. Today, typically 10 to 15 volts, then convert down to 1 volt. And so that means we have a current flow, which is lateral at that point. And we will see more and more the trend to go to a vertical one. Why? Because the last inch of this solution is acting as a bottleneck, right? And knowing that the number of power demand goes up like this, we have to do something against it. And a good way is to increase efficiency, go from a lateral power flow to a vertical one. So if you check this, now the last stage, the power module is just below the GPU, as close as possible, close to the point of load, including also the cores. The cores have a very important function here because they have a mechanical function, they have a thermal function, and of course they have an electrical functions. And avoid capacitance as good as possible. On the other hand, you have to find a solution to cope with the dynamics of the GPU, and that means increase the frequency of those DC-DCs. And therefore, you see a trend going from typical silicon MOSFETs more to GaN power switches. Let's talk about automotive. So there is a huge transformation going on at the moment. I would say it's fair to say that in the next 5 years, there will be more changes than the last 20 years. The car of the future will be always connected, always online, very user-centric. That means with software update, you can update your features, and in this way, the car stays somehow modern. It will be automated, so going to autonomous driving, and it will be more and more electrical. And so that means we need semiconductors to support it, to drive the digitalization, but also to drive the decarbonization. There are numbers telling us 25% of CO2 is just because of transformation. And if we have the chance to reduce it down to 0 by the electrification, I like this very much, and I like to be part of it. Now, why do we need to go to a so-called software-defined vehicle? Basically, you might see a trend of software-defined things. Software-defined vehicle is one part of it. The reason is just what I mentioned. We have the capability of the car gets autonomous driving, it gets full connected. So that means we need solutions which enable and ensure high compute performance, but also we want to have secure solutions, we want to have safe solutions, we want to have reliable solutions. And this is enabled by the software-defined vehicle. And the car manufacturer now move from a more decentralized solution where there are sensors all over the place, there are microcontrollers all over the place, to a more centralized solution. The final architecture solution will be the central car, but it does not happen overnight. So there are steps in between, and currently we are more in the mixed domain and zone architecture domain. So this is, if you buy a new car, that most likely will be with an architecture looking like this, and 2030, 2035, it will look like that one. And so this new EE architecture is crucial for software-defined vehicles. Already the architecture of the car today is very complex. We have more than 100 ECUs. We have cables of 5 kilometers. We have data communication of 20-25 gigabit per hour over the network in the car, but it's still not enough. It's still not enough to enable autonomous driving. And very interesting, where we see the trend of a centralization of all the signal and data processing, we see a decentralization of the power conversion. And the reason is the central car needs to be powered reliably and dependable. Dependable means that you always can rely on it, even if there's a fault somewhere. It needs to be detected by a diagnostic, and then within milliseconds, it needs to be, the power conversion and the power generation needs to be replaced then by an alternative solution. So it needs smart power management, right? Now have a look on the hardware challenge. Because of the increasing demand of compute performance and of the connectivity between ICs within the car, but also from car to car, but also from car to infrastructure, we see those numbers. And this is not just a factor of 2 or 3, I think it's incredible. CPU performance, 37, graphics, 39, memory size, factor of 8, and so on and so on. So, and here it needs solutions, and not only to provide the solutions as such, what comes on top is that if you look on how fast, in particular on the Asian market, new cars appear on the market year by year by year, it also requires development of such semiconductors in the same time frame. And honestly, in Europe, we are not there yet. So we are in the range of 3 to 5 years. But having time to market solutions, so the right product with the right requirements on time on the market is essential to be competitive. And that means in order to do semiconductors designs, then it's not only find the power performance right solutions to a low cost, but also bring it really fast to the market. And this has impact on the architectures and the tooling and the methodology, so on the whole ecosystem, and I come to this soon. So in a car, there are a lot of semiconductors because we have a lot of applications, a lot of use cases with different requirements. So it needs somehow solutions for motor drive, power conversion. It needs solutions to lift the window. It needs solutions to control motors, e-drives, most likely in real time. And as with autonomous driving, you get more and more sensors in the car because it replaces the human being sensors. So we talk about radars, we talk about cameras, we talk about lidars. So all those data needs to be processed. And that's why MPUs get more and more common getting into the car. And depending on the application, depending on the features, the products do have particular technologies. And this graph shows you how it develops over the year. So if you look on the semiconductors, typically the node of today's solutions of the MOSFETs is in the range of 500 nanometer. So node means this is a minimal gate length of such a technology. Whereas for analog mixed signal circuitries, so where are some numbers of analog converters in, or digital analog converters, operation amplifiers. We have seen some examples today. Most likely in the range of 130 nanometers. So the microcontrollers of today in a car on the double-digit range, 40 nanometer down to 16, 12 nanometers, and the microprocessors for data processing, they are in the single-digit, 5 nanometer, some in the 3 nanometer, and 2 nanometer not yet, but just a matter of time. Now looking to the applications, the motor drive in this example, somewhere in the back, is silicon carbide is a typical example of power switches to enable the electric drive. Then we have, as an example for an analog mixed signal chip, it's a window lift. Or think about HMI, so human machine interface, like the touch screen, the touch display, or there are a lot of sensors, meanwhile, capacitive sensor on the steering wheel. The microcontroller, you find them still all over the place in the car. One example is ADAS, so the advanced driver assistance. And then in the middle of the car, the central car compute. And usually there is a high bandwidth interconnect from the central car compute to all the microcontrollers. Oh, I take this one. So we have the central car compute, and it needs a high communication between the microcontrollers, which are typically at the zones here and here and here and here. And therefore, Ethernet is coming more and more into the car, the so-called SPE, single pair Ethernet. Now, how does the technology match with the architecture in such chips? Starting again with the power MOSFET, I think that's very simple. So it's all about power. And this with high efficiency. So RDS on, low parasitics, that's the key, because we don't want to turn electrical power into heat. As we come to analog mixed signal IPs, what the key message I want to convey to you is that then we have an increased amount of analog, obviously, but also already some digital in the blue berry color one, and memories. So it could already be a circuitry, an IP, which is somehow self-contained. And going further down to the microcontroller, you see that the digital portion increases, the analog decreases, the power more or less is gone. And with the microprocessor, there's hardly any analog anymore. Maybe a bit for, we call it housekeeping, so to check temperatures and maybe pressure, to ensure a reliable and safe application. But it's all about digital and memory with on-chip and very important external memory. We saw this presentation this morning with, for example, external NVM. So let's have a look more on the microcontrollers. As the demand on compute performance goes up, and at the same time, there's also a demand to reduce the power consumption. This is a driver for moving into more advanced nodes. Yeah? It's not that we need somehow the performance. For sure, you can run a CPU with a higher clock rate in 22 compared to 28 or 12 compared to 22 nanometers. But the main driver is the performance power, right? And usually if you go to the next node, this factor improves by 2. And why is this so important? Because it allows that you can increase, for example, in a microcontroller, the performance, but you stay with the same package. And that means more or less you can offer the product with the same price as the last generation, but double of the performance in the features. And this is the trend to go. Now, the move into advanced nodes then, as a consequence, is a driver for chiplet. So one slide about chiplet. I mentioned one thing that we have also to look on how to improve R&D times, going from 3 to 5 years down to 1 or 1.5 years. And that means providing architectures with high amount of scalability and modularity. Because then we have the flexibility to build our products in a, let's say, family of use cases very fast. And this is still possible with monolithic approach, like putting memory, digital, and analog on, but we run more and more into limitations. Now, going to chiplet offers the opportunity to have more flexibility. So chiplet basically means the monolithic one and the functions of the monolithic one is distributed amongst different chiplets. And each chiplet serves a certain function. So each chiplet is not self-contained. You cannot sell it as a chip as own. But putting them all together, and they have communication among standardized interfaces, from an outside world, it has the same functionality and the same performance as, or similar performance as the monolithic one, but it has advantages in terms of R&D, because such tiles are predefined, pre-tested, and if there's a need to scale up memory or to scale up digital, you simply add those predefined tiles in the package. So the SoC design of the future is more or less getting the package design, the subset design in the package. And another advantage is that depending on the functionality and the performance, the technology which offers best features for this function can be chosen. So that means instead of having one process and technology serving analog, memory, and digital, you can go for the best choice of technologies with low parasitics, lower RFF noise, or low leakage for analog. And you do this, the best choice for digital, which mostly is the most advanced one, where you put digital on and SRAM, and you have a special one for memory. Let's go to robotics. This is the next big thing, the physical AI. You remember the graph from Jensen. And physical AI means that the software AI now operates in a physical world, where sensing and actuating gets real in real time. And I think what's getting very interesting is that now software engineers, AI software engineers, have also to understand much better about physics, but also the other way. So I mean, hardware engineers have to understand better about software, and bringing physics and mechanical engineering and electrical engineering together to build up one system which in, let's say, perfect harmony emulates the human body behavior. And for sure, there is no crystal ball. Those are some numbers how this market can be established, and there are forecasts saying in 2030, and I talk about humanoid robotics, there will be 1 million human robotics on the market, and 5 years later, 13, and so on. Maybe it's 20 or 35, 40. Let's see and wait. But I'm pretty sure the increase will be tremendous. Now, with this motivation, what are the main components, key components of such a humanoid robotics? And notice we still have chargers and battery management and motor control and sensors, and this is pretty much the same, so a lot of similarities what we have in the car, right? And if you remember the new EE architecture with the zone control, where we have the central car and the central computer in the middle and the zone control on the four edges of the car, you can think of very much the same in the robotics. You know? Somewhere the central compute here, and then you have the zones here and here and here and here. And that's why a lot of automotive semiconductor companies now try to get into this market. How does the architecture look like? Basically, this of course is high level, and the standard has not been developed yet. So it's all, I mean, there are samples outside, but what will be the standard in the future is still in a movement. But let's say we have 3 pillars, right? So there's the pillar for the sensors and environmental sensors. Those are the sensors needed so that the robot can move through a room. And movement is described by position, by direction, by speed, and by torque. And then we have the actuators, because we want to move joints, arms, legs. So it goes with a lot of sensors and the actuators. And in the middle we have the decision system. So to say the brain of the compute, where all the data come together, and this decision system continuously sends the data, takes decision, calculates, and drives then the actuators. And this has to be done in a very synchronized way, because we have a lot of motors in the robotics, and we want to have very smooth movement. So if the arm is circling, you want to have something like this, what reminds us to the human being behavior, and not something like this. And in order to achieve this, we need synchronization between the smart actuators. And that's why also Ethernet becomes a very important component in robotics. And there might be a lot of different architectures, decentralized and centralized, coming up. I think decentralized will be a very common one. Why? Because then the motor control is very close to the actuator, so to the motor itself, and this reduces complexity, that reduces weight. It makes things more compact, and that's very important in robotics solution. So we want to also control the movement in a very predictable way, in a very fast way, in a very accurate way. And that means we need somehow components which support this, like MCUs with real-time capabilities, so fast ADCs, but also fast peripherals. We need the sensors which work accurate enough. And again, here you see all the different connectivities like EtherCAT. EtherCAT is actually very used standard in the industry to enable low latency connectivity. If the data rate increases, we for sure move more into the SPE, so Ethernet solutions. Now let's have a look on the MOSFET GaN. That's now my last slide. And I would like to explain you or give an argument why GaN is attractive in the motor drive. And I explain this by the phase current. Yeah, you already explained, Bernhard, that by increasing the frequency, components get smaller and you have smaller parasitics, so you have better efficiency. But what's also important, in particular with robotics, is the phase current. And what you see on the left-hand side is so the so-called FOC. This stands for the field-oriented control. So this is somehow is a control. Also, we have a feedback, a negative feedback loop here. So this from the sensor, which can be a position sensor, current sensor, over microcontroller, over gate driver, over power switches, and then feed it back. And this all has to be controlled by an algorithm running on a certain frequency. In this case, it's 20 kilohertz with silicon MOSFET. It works, but with the opportunity going up to 100 kilohertz, so improved by a factor of 10, we have less current phase noise. And that means, as a conclusion, that the dynamics of such a motor is improved. And this is what we want in the robotics, because then the movement even looks more smooth than with the silicon MOSFETs. That brings me to my summary. So what are the drivers for innovation? yeah, those are the three big topics. It's about HPC, the high performance compute. It's automotive, to make somehow the car drive autonomous, which you already could consider as a roboter. And the final one, the robotics, is number 3, the physical AI, and I think it will be tremendous what will come in the future. The software-defined vehicle is somehow the prerequisite to make autonomous driving possible. And it needs not only power management, but smart power management. Why? Because with autonomous driving, the dependability, which includes safety, security, and also reliability, is of utmost importance. So what else? Yes, so the increase of compute performance demand is a driver always move into the next node. And it's the performance power that is of important, not only power, not only performance, the ratio it is to attractive cost. And the driver for chiplet is then the driver of the advanced nodes. So that's my conclusion. Some references if you're interested in, and not missing the acknowledgement. So some of my colleagues which helped to bring up and set up this presentation. Thanks a lot, and do we still have some time for Q&A, or? Probably not. Okay, so I'm available, and I'm happy to answer your questions whenever they are. Thanks a lot.